Here's what we did in class today. We went to the applications that are on the TI-84 graphic document and we said, hey, let's roll a 10-sided die 50 times. So by golly, we did. We rolled that puppy 51 times and boom, there were the results. Not that this isn't the most exciting, cool thing in the world to do, but instead of doing it on there, we could just go to a list and simulate the rolls. But what I want to point out is that the population should be evenly distributed. Every number is equally likely to happen. But in a sample, it's not going to work that way. There's going to be chance fluctuation. Instead of using the application of rolling dice on the calculator, let's just go to a list. So let's go to Stat, let's go into a list, and let's clear that list out. So we'll hit Clear and Enter and clear the list out. And then with the cursor back there, we can hit the Math key, go to the Probability menu, and select Random Int, option 5. And then we're just going to type in, hey, we want numbers from 1 through 10, we want 50 of them. So we're going to paste them in the list, and boom, each one of my students then is coming up with a sample of 50 rolls of a 10-sided die. Then what we did was we said, okay, each student should then go and calculate the statistics for this bad boy. I want you to get your sample mean. And then what we did was, once we each got our sample means, here mine was 5.84, we put them on board. Now it's not all that pretty, but here was the data from 3 different AP Stat classes today, and instead of those being X's, they all should really be sample means, X bar. Now what we realize is that the population distribution looks like that, but when we take samples of at least 30, the sample means are going to be distributed normally. Now, what I did at that point was, I gave them this problem over here. It's basically find the probability of getting a mean of at most 5.3 if we roll a 10-sided die 50 times. And I gave them the mean and the standard deviation per one roll. Well, then we used the formulas to get that the standard deviation is 0.405 for the sample mean. So with that in mind, we drew the sampling distribution of means, the theoretical sampling distribution, which implies we don't even have to take a sample. We just know that if we do that work, that's the proportion of the time that you would expect to get a mean average less than, or at most rather, 5.3. Well, then what did we do? We came back over here and we said, what does all this have to do with anything? Well, here's what happened. We started with that distribution one at a time. That's the probability distribution of rolling a 10-sided die. But we plotted this data right here. Then we came back over here and we said, wait a minute, if the standard deviation of the sample means is 0.4, then if we go 3 standard deviations in each direction, we should expect all of our sample means to be from 4.3 to 6.7. Hey, wait a minute, did we predict the future? Is that exactly what happened when we took all these 75 samples? Bet your sweet bippy. The smallest mean was down at 4.3 and nothing got too terribly close to 6.7. And we said, but wait a minute, if we went 2 standard deviations over, shouldn't we be trapping 95% of our sample means between 4.7 and 6.3? Well, by golly, yes we should. So we went back over here and we put those cutoffs and we realized, yeah, we only had 3 or maybe 4. I think one student was demented and I don't know what that other little mark is on there. So we either had 3 or 4, and that's what we expected, that 3 or 4 of our sample means would be outside of that 95% interval. So we trapped about 95 or 96% in that interval. In other words, understanding statistics and probability is almost like having a crystal ball and predicting the future. We knew from the sampling distribution of means, from the theoretical distribution of means, what should happen, and then this data that we collected is called empirical data, but if we superimpose the theoretical sampling distribution, we see that sure enough, our empirical sample data behave very much like we would predict. Then I told the kids, if you're interested, let's catch a peek at what we're going to be doing in the next few weeks when we finish this sampling distribution unit where we're just still exploring the foundations of probability theory. Well, then what we're going to do is we're going to say, okay, Quinn got a mean of about 5.9 today. So I said, Quinn, let's suppose we rolled a die. We didn't tell you how many sides there were and what the numbers were, but you took a sample of 50 and you got a mean of 5.9. Now, without knowing the true mean, what's your estimate of where the true mean would be? Well, his best estimate is at about 5.9, but we can do something even more sophisticated. Check this out. If our sample mean should be within 2 standard deviations of the population mean, because the population mean's in the middle and our sample mean should be within 2, then it stands to reason that the true population mean is within 2 standard deviations either way from our sample mean. So if we had 2 standard deviations, we get 5.1 to 6.7. And this, you guys, is what we're going to be doing when we're constructing confidence intervals to estimate where the true unknown mean would be. Now, if we don't like that interval, 5.1 to 6.7, it's pretty big. We might as well have said, well, hey, it's somewhere between 0 and 5,000. We could do something to narrow that interval. And what would that something be? By golly, it would be to make the sample even larger, to make the standard deviation smaller, so that 2 standard deviations away would be an even narrower interval, and then we get more and more accuracy. So that's where we're headed, and that's why we want to be able to understand empirical data and theoretical sampling distributions and being able to calculate probabilities of results being at a certain location.